Okay, before we get started and dive into time dilation, we need to have a little discussion on dimensions. You can't talk about relativity without talking dimensions because that's pretty much what it's all about, is coordinate systems and dimensions. One thing I want to make clear is that when we're talking about dimensions in terms of relativity theory, we are talking about directions, not places. 1, 2, 3, 4 dimensions are talking about directions. And a lot of science fiction movies and TV shows, you see beings moving from our dimension into another dimension, or beings from another dimension coming here, and dimensions are depicted as places instead of directions. Well, in the context of relativity, do not try to think of a dimension as another place. It's another place that you can go or exist. That isn't what it is. It's a direction. It's a fourth direction. We have length, width, and height. Time is another direction. It's not another place. It's a direction. So let's just do a quick review here on our dimensions. Obviously, here we've got one dimension, very simple, x direction. There's no up or down. There's no other way. It's just this line. That's x. More familiar to everybody, probably from reading maps. I mean, who hasn't read a map at some point? We got xy direction. Now we're on a two-dimensional surface, or we got a two-dimensional construction here where we've got x and y coordinates, or it could be north and east, I guess would be this way. That's two-dimensional. We're all pretty familiar with that, and we're looking at a two-dimensional screen right now, so very easy. Also very easy is three dimensions, because that's what we deal with every day. We get up, and when we move around in three dimensions. We go forward, back, we go left, right, we go up, down, maybe we fly in an airplane or something, but we're very familiar and very comfortable with the three dimensions. And then what we do is we separate time from the three dimensions, and we have a clock to tell us what time it is. But the thing about that is that's not really how the universe is constructed. It was found when scientists tried to do certain calculations, like they tried to calculate the orbit of Mercury, for example. And there was another experiment done back before Einstein. It was called the Michelson-Morley Experiment, for those who are interested. In any case, they could not explain the results of the experiment. They could not explain the orbit of Mercury. Everything they tried to do, the calculations didn't work. The equations gave the wrong answers. And so what do? Well, Einstein came along and he said, you know, it looks like what we have to do to make this work out is we need to take this time coordinate and treat time as just like another direction. And we're going to take that. So he took that time direction and he incorporated it with the three dimensions of space. He added it to them to create a four-dimensional entity that we call space-time. So I want to take just a minute here or so to go over how he did that mathematically. And this is not complicated. Again, don't run away, but here we go. So when we're talking about distances in two-dimensional space, like on a map, if you want the distance between 2 points, it's the good old Pythagorean theorem from high school. We're going to go over that again in the next video. But for right now, just remember that in high school or even junior high, we learned that in a right triangle, like we have over here, that if you take x squared plus y squared, it will equal the distance here squared. So whatever x is, whatever y is, you square them, add them together, and you get this distance here squared. So if you want to just know what this distance is, you square x, you square y, and you take the square root. That's it. And that gives you this dimension here. And now that's in two dimensions. So when we're talking about dimensions, and this is the takeaway from this, is to understand what we mean when we're talking about dimensions. Here we have x squared. That's one dimension. X is a dimension. Y is a dimension. But this is only two-dimensional. So that's fine. That makes our triangle. Then in our more familiar three-dimensional space that we experience every day, you have an up, down, left, right, forward, back. That's x, y, z. That's three dimensions. So what did Einstein do? He took an equation similar to that, like this one right here, And all he did was turn it into a 4-dimensional equation. He took the 3 dimensions of space and added a dimension of time. So it looks like this. So this is essentially the distance in 4-dimensional space. Now, in actual relativity, for those of you who are familiar with it, the equation looks a little bit different than this. It's what they call a hyperbolic equation. I'm sure you're familiar with hyperbolic geometry if you're familiar with relativity. But for everybody else, let's not worry about that if you don't know what that means. Just realize that we can go from here's 2 dimensions in an equation, here's 3 dimensions, and here's a 4-dimensional space-time type equation. And each of these dimensions is a direction. It is not a place. As you can see, it is a direction. So please keep that in mind, and that's what our dimensions are all about here. Now, when we draw our space-time, our 4-dimensional space-time, we can't do that on a 2-dimensional surface. So what we have to do is, in order to make it work, we eliminate 2 spatial dimensions, which I've shown here. We just cross out the y and the z, or we can cross out the x and the y. It doesn't matter which one. What we need is 1 space dimension and 1 time dimension in order for us to illustrate time dilation. So by doing that, we limit motion, like it says here, to just 1 spatial dimension and 1 time dimension. But this will not change the results of any calculations that we do or concepts we present. You only need 1 space dimension and 1 time dimension to understand how time dilation works from a conceptual standpoint. Everything that happens in space-time. And space-time is just a unification of the 3 dimensions of space with 1 dimension of time. And when you try to draw that on a piece of paper or on a screen, here's what you get. You get a time axis because we want to be able to visualize that. And then we need a space axis. It doesn't matter too much which one we choose. It's just we need something to represent space. And that's what we've got down here. We are representing a spatial dimension. So this is how space-time looks. And it was constructed by Einstein by merging space and time together. Incidentally, you probably didn't realize that you already knew that. Because when you're probably talking to your friends and you say, hey, I want to go from here to some store. And you say, how far is it to that store? One of your friends might say, well, it's about 5 miles. The other friend might say, well, it's about 10 minutes. In either case, the time and space are equivalent with each other. You can use units of seconds for distance, and you can use units of feet for time. And we're going to get into that a little bit later. But for right now, the thing to remember that's really important is that dimensions are directions, not places. And Einstein constructed a 4-dimensional space-time because this axis actually represents all 3 of these axes. We just picked one, but that's the space. And then there's the 4th dimension of time. They are directions. They are perpendicular or at 90-degree angles to each other. And I think you can see that. I don't think there's anything here that is too difficult. It's everything here everybody experiences all the time. This is the one we're going to be dealing with as we go into the next videos and into the future here. No pun intended about the future, but we're going to, as we go forward into the future, this is the diagram we're going to be using for the most part. And that is going to show us in a very simple way how time dilation works. So that's pretty much concludes our review of space-time. So let's move on and take a look at vectors and coordinate systems. Again, please don't run away or shut this off. It's not going to get complicated. The whole idea of this series of videos I'm doing is to keep this as simple as possible, and so that people can understand these concepts without having to go through all kinds of mathematics. You can do this visually, and that's what I want to do. So please come back for the next one, and when you're done with this, you'll understand how time dilation works.